What's up, wizards? I've got a treat for you today. I've been building a lot of stuff with TypeScript and AI recently. I've been building agents, workflows, custom scripts, and CLIs to help me work faster and smarter. And Vercel's AI SDK has been an amazing tool in my toolkit. It's a library that solves a lot of the pain points when you're interacting with LLMs. And in this massive video, I'm going to give you a full tutorial on how to get to grips with it. We're going to cover prompting, streaming text, structured outputs, handling images and files, tool calling, and building agents. Is this a sponsored video? No. You don't need to pay Vercel any money to use the AI SDK. You don't need a cloud platform. You don't even need to use Next.js. You can use the AI SDK anywhere JavaScript runs. And that's why I'm so excited about it. It's so versatile, so powerful, and it's just the right level of abstraction for almost any AI task. This video is split into many different parts. Each part teaches you one or two things about the AI SDK. If you want access to the code, I strongly recommend you check out the hosted version on AI Hero instead. It's got all of these beautiful code samples as well as links to a GitHub repo where you can run this all locally. It also splits up all the videos into individual URLs so that you can reference them easily. So if you want that, go to the description below and head there now. But if you want the full YouTube experience, let's freaking go. There's a pretty common problem when you're building AI-powered apps. Let's say that you're using OpenAI as your LLM provider. You build all of this code here just to talk to OpenAI's API. And one day you think, oh, why don't we try Anthropic instead? But there's a problem. Anthropic's API is a little bit different to OpenAI's. This is especially true for things like streaming, structured output, tool calling. So you need to build all of this extra glue code just in order to try out a different model. The AI SDK solves this problem. It's a library you can call which handles the interaction between you and your LLM. So now you can call the AI SDK instead and it will handle all of the glue code. Not only that, but it has some really nice helpers for common use cases. It helps you stream text, do structured outputs, tool calling, and even handle agents. I think of it like the TypeScript standard library for working with AI. The AI SDK is maintained by Vercel, but you don't need to use Vercel in order to use it. You don't need to pay Vercel any money. It's free open source software. There are three different parts of the AI SDK. The first is the core. This is used for your backend code, so Node, Bun, whatever. You also have the AI SDK UI, which is a set of framework agnostic hooks and components. This is for linking up a front end to an AI SDK backend. There's also the AI SDK RSC, which is their React server components offering. This is for doing things like generative UI, all that stuff. This tutorial is just going to focus on the core. It's going to fill you in on the basics and give you the grounding to build virtually anything. It has maybe the best npm package name of all time, which is npm install AI. All of the core stuff is under the AI package. And you can integrate with different providers by installing their custom package. For instance, OpenAI is an AI SDK OpenAI, and then you can choose your model by calling OpenAI and then passing in the model that you want. So that is the lay of the land. You get a unified API where you can drop models in and out. You can stream text, generate text, work with structured outputs, tool calls, and then build agentic loops. And we're going to cover all of that in this tutorial. Let's start with the absolute basics, generate text. Let's look at literally the simplest setup that the AI SDK supports, using an LLM to generate text. We're first going to grab our model from Anthropic. In our case, we're going to use the latest version of Haiku. Now we're going to create a function called answer my question, which is going to take in a prompt. Next, we're going to grab the function generateText from the AI package. I'm in the AI Hero repo, which I have already downloaded AI SDK Anthropic and the AI package, so I'm good to go. Inside our function, which you'll notice is asynchronous, we're going to await the result of generateText, passing our model and the prompt. This is going to return us an object that contains a text property, which is a string. We're then going to return text from our function. Let's ask it a question. We're going to ask it, what is the chemical formula for dihydrogen monoxide? When we run this, it's going to call Anthropic with our query and return the generated text, logging it to the console. The chemical formula for dihydrogen monoxide is H2O. Lovely. I've got an Anthropic API key in my environment variables, which is being picked up by the script I'm using to run this. You can find all the instructions for setting that up inside the AI Hero repo. It's not only text that we get back from generateText, there's also a bunch of other stuff in here which we'll cover in our later examples. But that is the simplest possible demo for the AI SDK. We declared our model, in this case Anthropic's Haiku. We grabbed generateText from AI. We called it using the model and the prompt. We console logged the text, and so we were able to ask it a question and get back an answer. Very cool. That is but a mere glimpse of the power that is at our disposal. In our previous example, we saw how you can generate text using the AI SDK, but this spits out all the text all at once right at the end. What if we need to stream the text in token by token? For that, we can use the streamText function from the AI SDK. This takes in a model and a prompt in exactly the same way, but instead of returning text, it returns a text stream. The text stream is an async iterable. That means it can be streamed to a file or over a network connection. In this example, we're just going to stream it to standard out. This for await loop waits for every chunk of the text stream and then puts it directly into standard out. Let's say we ask it, what is the color of the sun? If we run this code, we're now going to see it streaming to our console. And from here, it's pretty easy to imagine just hooking this up to a network request and just streaming it to a UI. The streamText function also returns a text promise. This means if you just want access to the final text, you can just await text. So this is a nice option to have if you want to have access to both the stream and the final generated text. Sometimes you need the AI to act in a certain way no matter which prompt it receives. In this example, we're building a text summarizer, and so we want the AI to summarize the text that it receives. We want to give it a role, we want to give it instructions, and we want to do all of that before it receives the prompt from the user. To do that, we can use a system prompt. Doing that in Vercel's AI SDK is as simple as passing a system property. Under the hood, this prepends a special message with the role of system that has our system prompt in it. We could do that in the AI SDK as well if we want to. We can get rid of both prompt and system and instead pass a messages array. So this is what a system prompt looks like under the hood. This can be done in generateText, streamText, and all of the other APIs that we're going to look at throughout these examples. Using system prompts is one of the key tools for working with LLMs, so it's really nice that the AI SDK makes it that easy. I wanted to demonstrate for you just how flexible the AI SDK is when it comes to model selection. Here we have an ask function that takes in a prompt and a model of type language model. We can call this function with any model that the AI SDK provides. Let's say we create a prompt here, then we grab Anthropic from AI SDK Anthropic. Now we can pass that into ask by just having the prompt passed in and then Anthropic calling it with the model we want to select. If we want to call it with a different model, well, we can just call it with an OpenAI model, which we can get from the AI SDK OpenAI package. This just gives you a ton of flexibility with how you want to build your application. The ask function is totally decoupled from the model that it uses. So this type of language model that's exposed by the AI SDK basically lets you do dependency injection. You can inject any model into any system and it will just work. To me, this flexibility is one of the core selling points of the AI SDK. It's pretty normal if you're building any kind of chatbot to want to keep track of the conversation history. This is so the LLM has context over the conversation you already had, so you can ask follow-up questions without having to rephrase your question every time. Not only that, but understanding how conversations are persisted is really important for communicating with an LLM over the wire. And we're going to show how to do that with the Vercel AI SDK in this example. Let's start by understanding what the shape of a conversation history might look like. The AI SDK exposes a type called core message. This is an object that represents a message in a conversation. And if we understand this one type, I promise we'll understand everything about conversation history. So we've created an array of messages saying that this is an array of core message. Core here just refers to the fact that we're in the AI SDK core instead of AI SDK UI or RSC. Every message has to contain a role property. This is a string that can be assistant, system, tool, or user. Let's say that it's user for now. We also need to add the content of the message. For instance, the content of this message is the user saying hello you. To represent the LLM replying, we can use the assistant role. So again, in this conversation, we have the user saying hello you, and the assistant, the LLM, saying hi there. We had a brief look at system prompts earlier. They're represented in the message history via a role of system. In this case, we're telling the LLM that you are a friendly greeter, greet everyone who comes by. And the final role of tools here will investigate that when we look at tool calling later. As the conversation gets longer and longer, more user and assistant messages are going to be appended to these messages. And this simple array with these different roles and different content parts is basically all you need to represent a conversation. Now we understand understand about what the messages array is, let's apply it to a real-world-ish situation. For the first time here, we're actually going to spin up a server to give us a kind of server boundary to work around. We're going to put our server inside a start server function. We're going to grab the Hono package, and then create a new app inside our start server function. We'll add a root to our server. Then we're going to grab serve from Hono node server, and then serve it inside our start server function. We need to wait until the server is listening before we can make requests to it. For that, we're going to need to listen for the listening event. This is a great tip here. You can actually grab once from node events, and then inside start server, just after the server's been declared, we can await once server listening. So declaratively, this will just wait for the listening event to fire. Very nice. Finally, we're going to return server from start server. Next, let's build the API call. Our API get completions route is going to accept an array of core messages from AI. Since this is just a demo, I'm not doing any actual validation here. It's just going to be assumed that this is what you're going to pass. Then we're going to take those messages, which is the message history, and we're going to pass them into generateText from AI, as well as a model that I've got earlier. This means that based on the conversation history that it's going to receive from messages, the LLM will work out what to say next. The messages that it suggests will be added to result.response.messages. So from our API endpoint, we can return those as JSON using ctx.json. To some of them, we've created a little server endpoint that receives a bunch of messages and then returns what the next message should be. This is a pretty common pattern. It means our server is completely stateless. The client is responsible for tracking the messages and working out which messages it should send next. There are other ways of doing this, like your client could send just the new message and the server could maintain the state of the message history. But the way we've got it working right now, where the client keeps control of the messages, is kind of fine for a demo. Now that we've created our server, let's actually call it from the client. We're going to create a new array of messages to send, asking what's the capital of Wales. We're also going to start our server here, importing it from server.ts. We're then going to fetch from our server. We're fetching from localhost 4317 with an API get completions with a method of post, passing the messages to send as a body JSON stringified. Then with the result coming back, we pass it into JSON, and we know that it's coming back as an array of core messages again. Since these are only the new messages, let's concatenate them with all of the messages, so the previous messages we were sending, and then log them out. And when we run this, we get an output that looks like this. Our original question here has been appended to with the role of assistant answering the question. And this messages array is ready to receive more messages to keep on adding to the conversation history. In this example, we've seen how to keep track of a conversation history using the Vercel AI SDK. We've learned about the messages array, including all of the various roles. And we've also seen a pattern where you pass all of the messages to a server that can then append the newest message to the end. Well done for sticking with me on that one. That was quite some journey. You can use Vercel's AI SDK to connect to locally running models. In fact, not just locally running ones, but ones hosted at any URL. The AI SDK has a function called create OpenAI compatible. This lets you communicate with models that have an OpenAI compatible API. In our case, I'm using an app called LM Studio, which exposes this API on localhost 1234. So I can install AI SDK OpenAI compatible and create this LM Studio provider. I can then use this provider to grab a model. I'm using an empty string here because if you pass an empty string, it will default to the model you have selected in LM Studio. I can then use this model by passing it into generateText. So it works just like the OpenAI Anthropic models we've seen. I've specified max retries as 0 here. By default, the SDK will retry queries multiple times, I think 3 by default, just to make things more robust. But since the model is on our local network, we want it to fail instantly if it can't get through. Let's give this a go. We're going to ask the LLM a story about its grandmother. And if we run this, we get this quite detailed story about Nana's love for cooking. Good old LLMs. So this is a nice simple setup for how you can connect the Vercel AI SDK to a local model. Often, the thing that you want to get back from your LLMs is not text, but some kind of object. A classic example is data extraction, where you want to extract multiple properties from a single input. Let's say you're scanning a bank balance for the account number and the current balance. The most efficient way to do this is with structured outputs. This lets you ask the LLM a question, give it a format, and it will reply in that format. In this example, we're going to ask the LLM for a recipe. We want the name of the recipe, the ingredients for the recipe, which are objects inside an array, and then the steps to create this recipe. The first step is to create a XOD schema which represents the object that we want to get back. You can see that we've got name, ingredients, and steps here all declared in their XOD equivalents. If you've never seen XOD before, then I have a free tutorial on my sister site Total TypeScript, which I'll link to below. We can then take this schema and pass it directly into a function called generateObject from AI. This is receiving our model, the prompt, and the schema. Let's also add a simple system prompt to create recipe just to give the LLM a bit more context. The result that comes back from generateObject has a property called object, which contains our recipe. And thanks to TypeScript being clever, we actually get all of the properties auto-completed for us. Not only does XOD describe what object we want to the LLM, it also guarantees that the object is that shape when it comes back. So we can be pretty sure that recipe.name will definitely be defined, which is very, very useful. But we're not quite done here. We should provide the LLM with more information as to what each property actually means. Currently, all it's got to go on are name, ingredients, and steps here. We can do this by adding XOD's.describe function to each of these properties. Now it's clear to the AI what we're asking for when we're talking about each property. This is especially useful when the names are a little bit ambiguous or not that descriptive. And finally, we can pass a schema name to the generateObject function itself. We could also provide schema description here, but I think in this case it feels a bit like overkill. So let's give this a go and see what outputs we get. Let's ask it how to create baba ganoush. And when we run this, we're going to get back a recipe for baba ganoush. So there we go. That's how we get structured outputs from Vercel's AI SDK. We use generateObject instead of generateText. We pass it a schema with a XOD schema, and we use schema name, descriptions, and the .describe function to describe what we're doing to the LLM. Structured outputs are incredibly useful, and it's great the AI SDK makes it so easy. In our previous example, I showed you how to get structured outputs from an LLM, but the outputs were all generated at once. We waited for a little bit, we twiddled our thumbs, and then we just saw all the outputs all at once. This is because we were using generateObject here. But what if you want to see the object as it's being generated? What if you want to stream the object? Well, you can do that by changing generateObject to streamObject here. You'll notice a couple of changes here from the previous example. First of all, because we're now using stream, we have to wait for the final result. So result.object has now become a promise that we await for the final object. The reason for that is that streamObject returns the first chunk of the object as soon as the chunks come in. So the result doesn't have the final object yet. So we've got to await it. If we want access to the object as it's being generated, we can use result.partialObjectStream. This is an async iterable, meaning we can wait for each chunk to come in with a for await loop and then log it to the console. We're going to clear the console first and then console.dir it, so it should see it streaming in live. Let's give this a crack and see what updates we get. We're going to ask it how to make hummus. When we run this, the objects are being generated as we go. Woof! Did you see that? That was fast, but you notice there was progress as we went through. Let's try this one more time and whew, there it goes. Beautiful. The final chunk then of this stream, the result.partialObjectStream, is the entire completed object. So the way you'd use this in an application is instead of just logging it to the console, you would send these chunks over the network. That way your users could see the object being built up in real time. It's always nicer to see a progress indicator rather than just waiting and having it spat out at the end. So that's what the streamObject function does in the AI SDK. It's a really nice user-friendly API for building up objects over time. Another classic use case for LLMs is classification. That is classifying things into different categories. Let's say we want to take a user's comment here, pass it to the LLM, and then get back one of three strings, positive, negative, or neutral. In traditional software parlance, this is called an enum, a set of enumerated values. To do this, we're not only going to pass the user comment, but also describe the structured output we want back from the LLM. And to do that, we're going to use the AI SDK. We're going to start with a classify sentiment function. And inside it, we're going to call generateObject from the Vercel AI SDK. The difference here is that we're passing an output of enum. We can also then pass an enum property describing the enumerated members of this enum. The result we get back from generateObject contains an object property, as we've seen before, and this object, confusingly, is our enum. We can see that it has the type of positive, negative, or neutral. Let's try out a few different statements to see how it works. We can start with I'm not sure how I feel. And if we run this, I'm not sure how I feel comes out as neutral. Let's try this is terrible. And as expected, this comes out as negative. And just like that, we've got a pretty simple sentiment analysis system. We use generateObject from the AI SDK, passing it an output of enum, passed it the enum, and then just ran some text through it. This is a really great use case for enums, and it's great that the AI SDK makes it so simple. This simple primitive can be used for all sorts of classification tasks. Another thing that the AI SDK handles out of the box is passing images and files to LLMs. You can take this file, pass it to the LLM, then the LLM can return text or images or call tools with it. It's an extremely powerful feature. Not all LLMs support it, but for the ones that do, the Vercel AI SDK lets you handle it. In our case, we want to pass an image to the LLM and make it generate a description that we're going to use as alt text for that image. Alt text can be used on a website or an app to describe an image for folks that can't actually see it. We're going to start by using a pretty simple system prompt saying we don't want to pass 160 characters, use simple language, be concise, and create an alt text for the image. We're then going to create a function called describeImage, which is going to receive an image path on our local file system. This looks fine, but we're not actually using the image path yet inside our function. We can't use the image path directly as a prompt. We first need to load the image into memory and then pass that binary into generateText. To load it into memory, we're going to grab readFileSync from Node.js. This stores the image in memory as a uintate array, which is basically a raw binary representation of the image. For the Node nerds out there, yes, it's technically a buffer, but a buffer is just a uintate array with a few extra methods. We're using the sync version of the API here, but of course we could use readFile from FS promises if we wanted to, if we were really concerned about non-blocking I/O. But for this, readFileSync is perfectly fine. Now we've just got to find a way to pass this image as uintate array into generateText. We can't pass it in as a prompt directly, so we have to pass it in using the messages array. This is in the same format that we saw before when we looked at chat history, but here we now have a content array where we're passing a type of image, and the image is the image's uintate array. Let's try running this. I've got an image of some fireworks that I would like to test, and so I'm going to call describeImage using path.join to grab the local fireworks JPEG. And when we run this, we're going to get back a description of the image that we just saw. Colorful fireworks display over a city skyline at night. Spectators watch from the shoreline. It's like Tolstoy. To sum up then, we took an image, put it into memory using readFileSync, passed that in the messages array as a uintate array, and got back a description using generateText. Now our current approach works if you have the file in memory here, but what if you only have a URL to the file? Well, for that, there's a really nice shortcut we can use. Let's first change this to image URL instead. We no longer need to readFileSync it since we're not going to load it in memory. And then instead of passing image as uintate array, we're going to pass in new URL image URL. We're wrapping the image URL in new URL to indicate to the AI SDK that this is a URL we want to pass directly to the LLM. I've got an image here which I'm hosting on GitHub, so it's available at a public URL. I'm not sure where this is, but it looks very pretty. I would love to go there. And now instead of pointing at a local file, we're going to point at this URL. Let's see what happens when we run this. It's going to go to that URL, try to pull down that image, and then describe it for us. Lake Bled in Slovenia. Calm water reflects buildings and autumn trees. So there we go. New URL is a really nice shortcut you can take when you want to point to a URL that is publicly available. So just like that, we've built an alt text generator using the Vercel AI SDK, passing it through the messages array, and either passing a file in memory or locating a URL and passing it that URL. Extracting structured data out of unstructured data is one of the most powerful use cases for LLMs. In this example, we're going to be passing a PDF to an LLM and getting it to analyze it for us. In this case, it's going to be a PDF of an invoice, and we're going to extract all sorts of information like the currency, total amount, invoice number from that invoice. This structured data is going to be so much more useful than this unstructured PDF here. It means we can store these fields in a database, query them, filter them, all that stuff. By the way, this is the demo document that we're going to be analyzing. It has a dollar amount here. It's obvious it's from Australia because it's Australia fresh produce. It's got some addresses here, and it's got a detailed list of everything on the invoice. Since we need structured data to come back from the LLM, we're going to create a massive XOD schema. We've got the total, the currency, the invoice number, the company address, company name, and invoicee address, all with these .describe functions on them to basically say what these fields are. I know I've talked about these describe fields a lot, but oh my god, they're so important. This is prompt engineering. You are telling the LLM what these fields do, what it's supposed to be looking for in the document. Let's create an extract data from invoice function. Inside, we're going to call generateObject here, passing in our model, which is going to be Claude. Then we're going to use a system prompt, very simple one, and then passing in the schema. We're expecting an invoice path, which is going to be the path on our local file system to the PDF. In the example that we saw before, we passed messages into here and we passed an image into this content array. We can do the same thing with the PDF. We're still reading the invoice path, turning it into a uint8 array and passing that into data now. Instead of type of image, we now have a type of file instead. We also need to pass in a MIME type in here to tell the LLM what kind of file it's receiving. It could probably work this out on its own by just checking the magic numbers of the file, but you know, it's polite, isn't it? Finally, we're going to go back to generateObject up here and return the object from it. This object, just like before, matches the schema shape that we described above. Let's give this a go. I've got a path to the invoice, and when we run this, we get back the data from the invoice. We can see that the totals match 39.6, 39.6, the company address 123 Somewhere Street in Melbourne, and even the company name of Sunny Farm. And just like that, we've got a reusable function where we can extract the required data from any invoice. We use generateObject, passing it a schema, passing the file as a uint8 array to the messages array, passing a MIME type so it knew exactly what sort of file it was dealing with. Then we use structured outputs with a really detailed schema to get back structured data from unstructured inputs. It is wild how simple this is, given how difficult a problem this has been historically, but oh my god, you can do so much cool stuff with this. Anyway, that is how you pass files to LLMs using Vercel's AI SDK. Vercel's AI SDK has a really simple way to create embeddings. I'm going to assume that you know what embeddings are for the purposes of this video, but essentially they're a way to represent words, images, or data in high dimensional space. You can then compare them based on these dimensions to check how similar two things are to each other. This is called a semantic similarity comparison. This makes embeddings a really powerful primitive for things like search and categorization. In this exercise, we're going to be embedding some words in a very simple vector database. The first step is to grab the embedding model. The one we're using is from LM Studio. This is running on my local machine. If we wanted to use OpenAI instead, we would import it from OpenAI and call OpenAI.embedding. In this simple example, we're just going to embed some words: dog, cat, car, and bike. To create the embeddings, we're going to grab the embed many function from AI and then create the embeddings, passing in our local model and the values. Let's try running this to see what we've created here. We can see here that we've created an array of vectors. Now, each vector, there are 4 vectors, one for each word. Each one is an array of numbers. So we've got, I think, hundreds and hundreds of numbers, 668 more items in each vector. Each one of these numbers represents a dimension in multi-dimensional space. And so for each vector, there are 4 vectors, one for each word, we have over 668 different dimensions. And so thanks to the embed many function, we now have vectors for dog, cat, car, and bike inside embeddings. We're now going to collect these together into a very simple vector database. We're mapping over the embeddings here and then basically storing the embedding next to the value that it represents. So vector database ends up being just an array with the value, which is the string, and then the embedding, which is the vector that we saw. In the real world, you would store these in an actual database using something like Postgres and pgvector. But for small numbers of values, this is perfectly fine too. Let's now use our vector database. We're going to use it to search for the most similar word to a search term that we choose. To do that, we're going to have to embed one more word. So we'll grab embed from AI, and now we're going to embed our search term. So we're going to search for the most similar word to canine. If we look at search term here, then we've got search term.embedding, which is the same as all the vectors that we've got already. So now, amazingly, we have all the information we need. All we need to do now is a bit of maths, or sorry, math for my American listeners. We just need to go into our vector database, find the embedding which is most similar to our search term.embedding, and then return that. To compare these two vectors, the AI SDK exposes a cosine similarity function. So we can grab that from AI here, and now we're going to map over each member of our vector database and do something interesting. We're first just going to return the value, and then we're going to return how similar it is using cosine similarity. This takes in 2 parameters, the member of our vector database and the search term embedding. And then finally, we're just going to sort these by by similarity here using .sort. This should sort the most similar one to the top. When we run this, we can see the results here. Cosine similarity returns a number between 0 and 1, and so dog is the most semantically similar word to canine, and it turns out bike is the least similar. Interesting. If we change our search term here to feline, then we should see that cat is the most similar to feline. How about something like pedal? Well, none of these are very similar to pedal, but bike is the most similar, car is the next most similar. This relatively simple setup here can drive all sorts of awesome features like search and categorization. We grabbed our list of desired values here. We then created an embedding for each one. We loaded those into a vector database. We embedded a vector for our search term, in this case pedal, and then we mapped over the vector database using cosine similarity to compare the vector for the search term for the one in our database. This is so useful because you can just create the embedding when the entity is created, and then when you search for it, all you need to do is just embed your search term. This makes it a pretty efficient operation, and it's really nice that the AI SDK exposes the embed, embed many, and cosine similarity functions. So far, we've been getting LLMs to answer questions, scan documents, and do data extraction. But they can do a lot more than that. LLMs can interact with the world. The way they do that is alongside the prompt, giving them a set of tools they can call. And then the LLM describes which tools it would like to be called using tool calls. The results of those calls end up as tool results, which we can later, if we want to, pipe back into the LLM to feed it more information. But let's not get ahead of ourselves. For now, all we're going to do is build the simplest tool calling LLM imaginable. We're going to create the most expensive and pointless console log of all time. To get started, I'm going to grab my tool calling model. In this case, it's Haiku from Anthropic. I'm then going to grab the tool function from AI, and our tool is going to be called log to console tool. The first thing that any tool needs is the description of parameters that it's going to receive. This is done with a Zod schema, which in our case looks like this. We should also use describe really to make sure that the LLM understands what each parameter does. Next, we need to say what the tool is going to do. We do that by specifying an execute function. The execute function can be async, so it can virtually do anything. It can write to a database, it can call APIs, but in our case, it's just going to log to the console. And of course, this is really nicely type safe too. If we rename this to message, then it's going to be message instead. Next, we're going to add a description to the tool. This tells the LLM again what it's supposed to do with the tool. This is all prompt engineering. Now that our tool's been created, let's actually use it inside a generateText call. We're going to create a log to console function which receives a prompt and then pass that to generateText along with the model. We're going to give it a system prompt to rather dramatically, your only role in life is to log messages to the console. Tell it to log messages to the console. And finally, we can pass a record of different tools here, and we're going to say log to console is the log to console tool. So to recap, we have created a tool, we have passed it to generateText, and given it a simple system prompt to encourage it to use the tool. Let's try this out with the traditional greeting, and when we run it, we're going to see hello world being printed out to the console. Now, that's pretty good, but it's quite opaque what's happening here. How do we go in and debug this? We're going to grab the steps property out of generateText here. Steps is an array of each of the steps taken by the process. We can look into each step, see what was passed to the LLM, and see what tool calls and tool results were generated. For now, let's just go into steps, grab the first step, and then see what tool calls were called on it. When we run this, we can see that the tool name log to console was called. We can also see the arguments it was passed, args message hello world. If we were to try changing this to tool results instead, then we can see the result of our tool call. In this case, we didn't return anything, so the result is undefined. These tool results can be fed back into the LLM to make it more powerful, provide it more information, especially when run over multiple steps. So we've ended up with something pretty powerful here in very little code. We created a tool, grabbing the tool from AI. We gave it a description, a Zod object of parameters, and a function to execute. Note, by the way, the LLM itself isn't executing this. It's giving us the tool calls that it wants to happen, and we execute it. That's why console log is happening on our console, not Anthropic's console. Finally, we pass all of that to generateText along with the system prompt, and it logs to the console calling our tool. We can debug that by looking in steps and either looking at tool calls or tool results. So there we go, that's a really simple introduction to tool calls, which are an incredibly powerful primitive. In our previous example, we looked at tool calling, where you can pass the prompt as well as the tools to the LLM, and it will return you a set of calls that it wants you to make. In this example, we're going to look at what happens when you pipe the results of those tools back to the LLM. This can create a powerful feedback loop where the LLM is continually grounding itself in the real world, asking questions with its tools and receiving answers from tool results. And this feedback loop is what most people, including Anthropic, call agents. The Vercel AI SDK makes this concept of a loop super simple with something called steps. And we're going to make an agent that can retrieve the weather for us at a city we specify. To kick that off, we're going to use our small tool calling model, again Haiku. Then we're going to create our getWeather tool. We give it a description as well as some parameters. Now we're going to implement the execute function. In this case, we're just going to stub it out by always returning the same thing. The weather in the city that you specify is 25 degrees and sunny. But because it's async, if we wanted to, we could go away and actually call a weather API to get the actual weather for that city. Next, we're going to hook this tool up to a function called ask a question. We're going to call streamText with a model and a prompt and the tools. And then, like we've seen before with streamText, we're going to write the text stream to stand it out as it streams in. And finally, we're going to ask it what the weather's like in London. Now, when we run this, we notice something interesting. We don't actually get the information that we're looking for. It just says, I'm going to help you check the weather. Why would this be happening? Let's debug this with the same strategy we used before, grabbing steps from streamText. Instead of logging out the text stream, instead we're going to log steps. And because we're using streamText, we actually have to await the result of steps. Steps is a promise here. And here's what it spits out. There are several things to notice here. The first is that it only took one step. We can see that it called one tool here, getWeather, and it returned the result of the weather in London is 25 degrees and sunny. So it seemed like if we were just able to call the LLM again with the information in the tool, like take another step, it would be okay. In other words, it seems like the LLM got the result of the tool, but then it didn't feed it back to itself. So the question is, how do we create this loop here? How do we make the LLM take more than one step? The way to change this is to pass max steps to streamText, and we're going to specify as 2. This means that instead of stopping this loop after one iteration, it's actually going to go 2 iterations round. So the LLM will choose the tool calls, it will get the results back in the LLM, and then it will decide what to do again. I'm going to revert this code to what it was doing before so that we can see the stream. And when we run this now, we get a really cool output. We can see the first step here, and then it reacts to that information and even says that it sounds like a great day to be outside. Let's try something interesting now. What would happen if we set the max steps to 10? Turns out that we get nearly the same result. The LLM actually stops itself after 2 steps. I've done some debugging into the steps here, and on the second step we have a finish reason of stop. This means that the LLM itself actually decided, no, I have completed my task, it is time to stop. So max steps really operates as a safety mechanism. You can specify the lowest number really, but if you do specify something above it, then the LLM may itself decide to stop. But it's really not a good idea to specify something like infinity, because, you know, that might cost you a bundle. So to wrap up, we've seen how with one simple property, max steps, you can create an agentic loop where the result of your tool gets fed back into the LLM. This lets you create a gorgeous feedback loop where the LLM is continually grounding itself. And if you do this right, it makes hallucinations a lot less likely and makes the LLM a lot more useful. And that, folks, is my Vercel AI SDK tutorial. If you are hungry for more, there is only one place I recommend, and that is AI Hero. We're going to cover all sorts of stuff from evals to prompt engineering to RAG to agents. And in the future, I'll be diving into developer productivity too, creating your own coding agents and getting the most out of existing tools like Cursor. But mostly, I'm just really thankful to you. Thank you for getting to the end of my longest YouTube video ever. This really has been a ton of work to put together, and if you've enjoyed it, then please leave a like and hit subscribe. And if you want more of this stuff, then go hit up my newsletter on AI Hero. Thank you so much for joining along, and I will see you very soon.